Okay, we have a ping pong ball. Our ping pong ball is attached by a thread to the bottom of a beaker full of water. So we have a beaker full of water. Our ball is attached to the bottom. Now if that thread broke, the ping pong ball would go shooting out of the water. And that's because its density is less than the density of the water. Any object whose density is less than the density of the fluid it's in is going to float up above the water. Any object whose density is greater will sink. So as a side note, the reason for that, if I have an object floating, we'd have the force of gravity downwards and the buoyant force upwards. That means the buoyant force has to equal mg if it's floating. If the buoyant force is bigger than mg, then it's going to shoot upwards. If mg is bigger than force of buoyancy, it will go downwards. The buoyant force depends upon the density of the fluid, the volume in, and g. The mass of your object depends upon the density of the object times the volume of the object. G's cancel.
What's the second V object?
Yeah, V of the object. So V of the object over V of the fluid will equal the volume that's submerged in the fluid over the actual total volume of the object. If density of the object is bigger than the density of the fluid, then Vn has to be bigger than the V of the object to float. So it will be, basically it'll sink to the bottom.
So do we, I mean, this is a little advanced, but we don't consider fluid compressible for most things, right? So we don't consider that the fluid gets more dense.
Right, we're not worrying about the compressibility of the fluid. And water is nearly incompressible, so it's not a big deal to not worry about it. But you're right, we're not worrying about the change in density with depth. That's exactly right. This is actually kind of interesting. Icebergs. Big old icebergs, North Pole, South Pole, floating around. The density of the ice is like 9 something. Can someone look in the table really fast? Tell me the density of ice. 920? Density of the fluid is water, so it's between 1,000 and 1030. I'll say 1030 since they're out in the ocean. So 920 over 1030.
Well, is the seawater frozen or does it expel the...
It's just, it expels the impurities.
the impurities?
The volume of the iceberg in the water. Am I doing that right? Yeah. Is 89% of the actual volume of the whole object. You basically only see 10% of the entire iceberg, which really is kind of interesting when you think of how big some of those icebergs are. You're only seeing 10% of them.
So in a freshwater lake like that, we'd get a little less because it'd be 1,000.
This would be smaller, so we get a little bit higher of a percentage
yeah,
here.
like our glaciers coming down into a...
Right, in a freshwater lake, yeah. Okay, so for floating objects, the buoyant force has to equal mg. The less dense the object is, the higher it's going to float. The less there will be in submerged. which is always an interesting thing. I don't know if you've ever really thought about it, but a big old cargo ship or a big old cruise liner, those things are huge. Yet they're floating. And they have a decent amount of the volume outside. So why can they float? They're displacing more water, but why? I mean, if they're so massive,
They're not solid.
why are they sinking?
It doesn't go clear through.
Right. They're not solid objects. There's a lot of empty rooms with lots of air in them. This density of your object is the overall average density. That has to include all of the air in the spaces as well as the actual materials that make up the boat. So the overall density of the object, including all the empty spaces, is quite a bit smaller than the density of the water. That's why they float. Sorry, tangent. Let's go back to the original question. Back to our ping pong ball. Our ping pong ball is not floating. Do you agree with that? It's not floating. It's attached by a string to the bottom. If the ping pong ball was disconnected from that string, it would certainly pop up and float very high on water. Because it has a very small density. But the fact that the ping pong ball is submerged, the fact that it's in a fluid at all, means there is a buoyant force. Any object in a fluid will have a buoyant force acting on it, period, end of story. It doesn't matter where the object is. It doesn't matter if it's floating or it has sunk to the bottom. Any object in a fluid will have some sort of buoyant force. We have the force of tension in the string. Tension's pulling down on the ping pong ball. And we certainly have the force of gravity as well, acting downwards on the ping pong ball. So according to Newton's second law, we need to add up the forces. So we have the buoyant force minus the force of gravity minus the force of tension. That all has to equal ma, but what's the acceleration of our ping pong ball? 0. So those all have to add up to be 0. So the force of buoyancy depends upon the density of the water, the volume of the ball. The ball is completely submerged, so we need the entire volume of the ball, and it depends upon g. I'm going to bring the force of gravity and force of tension to the other side. Force of gravity depends upon the mass of the ball, and g, plus the force of tension, which we were given in the problem. So basically, our only unknown is the volume of the ball. So let's solve for it. We're going to have the mass of the ball. We need to put the mass in kilograms, though, for our units to work out properly. So 0.004 kilograms times 9.8 meters per second squared. Notice the g's didn't cancel. There wasn't a g in every term, so we couldn't cancel the g's out. Plus the force of tension, and the force of tension was given 0.028 newtons. All over the density of the water, which is 1,000 kilograms per cubic meter, times g, which is 9.8 meters per second squared. Now our units are meters cubed. The kilogram meters per second squared is a newton. So this term has newtons, this term's newtons, this is newtons per meter cubed. So all the newtons cancel. The meter cubed comes up to the top. So that's a very, very small volume. The ping pong balls aren't that big. We want to know the diameter of the ball. This is the volume of the ball. The ball happens to be a sphere. What's the equation for the volume of a sphere? Think about your units. Cubed. So 4/3 pi r cubed. So multiply by the 3, divide by the 4 pi, and then we need to take the cubed root of it. If you don't have a cubed root button on your calculator, remember the cubed root is the same thing as taking it to the 1/3 power. So I get a radius of 0.012 meters, so 1.2 centimeters. The diameter would be twice that, so 0.024 meters, or 2.4 centimeters for the diameter of our ping pong.